give a practical guide to Markov chain Monte Carlos. This is just basically going to be, once again, rules of thumb, little algorithms. There's no theory here. I will do this entire, this may be offensive to some of the people in the audience, but I'm going to do this entire thing without mentioning base theorem once. Yes, there are much higher experts in MCMC in the audience than me in Mackie. So if I say something totally abjectly wrong, please correct me. If I said something moderately wrong, just sit there.
Wins.
You can go. But I use MCMC a lot in a lot of my papers. It's just a very efficient way of exploring the posterior in a high-dimensional parameter space. But before, since this is supposed to be introductory to statistics, I think it's probably a good idea to actually mention what Monte Carlo means before actually going on to Markov chain Monte Carlo. Probably all of you know this, but let's just, Monte Carlo is basically just you're going to discretely sample from probably the distribution. So you got a set of points, and the distribution of this points is some predefined distribution. And a lot of different things you can do with Monte Carlo. Numerically solving integrals is generally the type of thing that I will do. An n-body simulation is basically a large Monte Carlo way of solving a bunch of n-coupled PDEs of the equations of motion. So, n-body simulations in the universe are basically large Monte Carlo simulations. So my example is just going to be a rather silly example, but it's kind of funny. It's how to calculate pi with Monte Carlo. So if I have a square which goes out to -1, 1 on all sides, I can just randomly sample. I can just randomly draw a bunch of points inside of this square, right? With some random number generator that I have, anywhere, right? I also know how to calculate the radius of a circle of R. So basically, by Monte Carlo, I'm going to say, and I know the ratio of the areas would be pi r squared over 4r squared. So if I just have, n number of Monte Carlo samplings inside of this square space, and then I will say, well, I'm only going to keep the ones that are inside of the circle. So I'll calculate, the distance from the origin for each one of the circles, and only keep the ones that have a radius less than 1. Right? So then the area of the circle is the number proportional to the number of points in the circle. The area of the square is the number proportional to the number of points in the square. And then pi is just going to be 4 times the number of points in the circle divided by the number of points total. And I did this in SM this morning and got an accuracy of 10 to the -3 with 10,000 random points. So possibly not the most efficient way to calculate pi.
Did the ancients ever use that one?
Yes, they could have. Actually, this is
because SM was back there.
That was their primary tool, after the compass and the straight edge.
Well, at least I didn't use COBOL. But you can do things like, say you wanted to know what the projected, projected surface density of like an NFW dark matter halo profile was. You didn't feel like doing the integral. You can just randomly sample from the NFW profile. And then let's say it's actually some triaxial thing, and it's got a rotation angle which is arbitrary with respect to the line of sight. Then you're really not interested in doing, doing the analytical integrals or whatever. And you can just, randomly sample inside of the density distribution that you've predefined, and then just, project all the points and count them up, and that's your profile. I end up doing this all the time just to check and make sure that my math is right. This is a good cross-check.
Can you explain where the name is coming from?
Once again, practical things that I should have been Wikipediaing the night before.
There's
Actually,
a
I have no
beautiful
idea.
city in
I think it was like Carlo Casino.
yeah, it's
Yeah,
named
but is it because of casinos? Because it's like random and casinos are random?
It's named after it. We've been trying to figure out how to run a conference on Monte Carlo here in Monte Carlo.
I'm sure it's been tried before.
But I mean, it should.
It's a beautiful town.
If there's something about the house always wins involving things a little bit more appropriate name. So, okay, that is a very basic introduction to Monte Carlo. Does anybody want to hear a little bit more about this or have specific questions about Monte Carlo integrals? There is an actual Monte Carlo integrator in numerical recipes that I've used before. If you have, some very high dimensional integral that just takes way too long to do and you have to do it a million times, sometimes this is a good idea. Any questions? All right, well, let's move on to MCMC then. So basically, MCMC is just this idea, MCMC. Once again, you're just going to randomly sample from some posterior of your, where theta is now your parameters in some model, given your data. All right, that's the closest I'm going to get to beta zero throughout the entire. Now, this basically scales as number of parameters that you linearly, number of parameters that you have. So obviously, if you just wanted to do some brute force grid, if it was 3 seconds per time you calculate your model, you have 7 parameters, and you wanted some 10 by 10 by 10 whatever, that would take a year to actually solve. Whereas on MCMC, depending on how smooth your likelihood surface is for your model, you can probably get through something like that in a day or two. So this is very easy to explore your parameter space in a very short amount of time. This is why this has become very, very, I would say, the dominant tool now for people trying to explore parameter spaces in high-dimensional models. I think it was introduced to us in this field by CMB people. You feel that's correct? The WMAP team really was very good for advertising MCMC to the rest of us. So there are many, many, many different ways of doing MCMC. I'm going to describe something called the Metropolis Algorithm. Might be the same as the Metropolis Hastings, I don't actually know. This is probably the most basic MCMC. It's no frills, no bells and whistles, but it's very easy to code up, very easy to implement, very easy to understand what's going on. And it's just for people that want to use this, there are tools available on the web that you can download. But as David and I were discussing, it's really very a good exercise for you to actually really create your own, because sometimes it's a lot easier for you to incorporate your own code into the model that you were actually trying to fit for, as opposed to like doing square peg round hole with somebody else's.
Can I just make one comment about this? There's one other important thing about MCMC, which is that you only ever have to evaluate ratios of that function. Yeah. That's key because I know you don't want to write Bayes' theorem on the board, but in Bayes' theorem there's this nasty denominator that you can't calculate. And so you never really know your function hot, you only know it up to a constant, and MCMC requires that. I think that's an additional reason we all love it. If it didn't have that property, it would suck.
Yes, if there was some unknown that you had to go out and calculate. So here's the basic idea of a Metropolis MCMC. So you have some starting position. Theta naught, and we'll call it theta I minus 1, because we're going to eventually go to a theta I, where I is the element in your chain. So calculate your likelihood. Let's call that L. X given theta I minus 1. And normally this just, for me at least, this just means calculating a chi-square time model. I'm sure there are different ways that you can do this calculation of the likelihood, but the most straightforward easy thing to do is just say that that's going to be your chi-square. So then you obtain your new set of parameters from what's called the proposal function, or the proposal distribution. And this, I generally call this Q in the notation of MCMC. I shouldn't ever say we when I say MCMC they. And it depends on So this is your new one, and it will depend on the old one. The idea is that the steps in the chain are supposed to be independent, or at least they're only dependent on the previous step. That is not exactly true, but we'll talk about that a little bit more and how to optimize your chains. So then you obviously calculate your likelihood of theta I. So then if likelihood of I minus 1 is greater than likelihood of I is greater than the likelihood of I minus 1, accept into the chain. And if the likelihood, well, we'll put it this way. If the likelihood of I is less than the likelihood of I minus 1, then you accept the probability given to the likelihood ratios. So, you know, in the Monte Carlo way, you draw some random number, u, which is some uniform from 0 to 1, and if it's less than this ratio, then you accept it. If it's greater than this ratio, if u is greater than, then you keep the next copy of I minus 1 as the ith copy of the chain. And then you go back to the beginning and you do this over and over and over again. Okay, this is really the basic idea. Very simple. Any questions or criticisms?
So this other condition where the likelihood of the new parameters is less than the previous one, you're kind of calculating a probability that will still get you the right parameters going forward, or that is the right parameter set. Like, how would you how do you describe what's going on here? So it's quite clear that you accept the likelihood is greater.
Right.
But yeah, how would you explain the second part?
Well, if you were only to do this step, then that would be basically like a chi-square minimum, right? You're only going to go down in chi-square or up, you know, up in the likelihood surface. But you want to explore the whole likelihood surface. So, you know, just think about what David said. These are all like likelihood ratios. You have two models, and you know what the ratio of your likelihoods is. Then, you know, a fraction of the time that model is actually going to be better is, you know, proportional to the likelihood ratios. And so you should accept that point in your chain, since you're going to try and get statistics of the posterior. You need to sample the lesser likelihood space part in that parameter space proportional to those likelihoods. Other questions? David.
Can you just put the else onto that? If, so if the if one condition, just say else, you keep the new theta I. I just want to have to make sure that algorithms keep moving forward.
Also, how are you going from theta I to theta I?
That is the key to the entire thing. You could actually do this in really dumb ways, and eventually you will get the right answer. You know, it just all of this is about then optimizing the convergence of the chain. So this is really the key to making everything work properly.
You know is wrong, but you actually decided to keep the recording.
It's a really good podcast.
So the method I'm describing is that each parameter in your set of parameters theta is changing at all times. So every step, every parameter changes. You can do weird variants where only a subset of the parameters change, or only a single parameter change. I believe that Cosmo MC, which is probably the most well-known and highly cited MCMC code out there, does subsets, and you know, it's really not necessary if you have a well-defined model. Okay.
Can you say why you're interested in the whole chain hidden, as opposed to just all going down and finding the lowest point, the highest likelihood?
Well, so the highest likelihood point, so your best fit model, right? So sometimes I take the lazy road, and I will use MCMC to find the best fit model. But mainly MCMC for the errors. MC, I will never admit to this in public paper.
There's a video camera rolling. just excited
I did not have
that you
relations
did
with that MCMC. I've totally lost my train of thought. The whole purpose is to get the uncertainties in all parameters, not to find the best fit model. MCMC is a highly inefficient way of finding the best fit model, just because you're always going to try and explore the other parts of parameters. There's a lot of volume out there in all of your parameter space, and so it's going to spend a lot of time in very low likelihood parts of the surface. So, what you would want to do is then change it such that you only take steps which you have an increased likelihood. That might be a slightly more efficient way of finding the best fit model. But there are lots of really good ways out there. Usually I just use the Powell method in my questions.
Can I add something?
Yes.
So the thing that you wrote at the beginning was the probability of the parameters of your physical model given some data. And at the end, your chain is a set of unbiased samples from that distribution. So if you take a histogram or something, that would give you the distribution of the parameters that are consistent with the data. And so that's why you want the whole thing. Like, it's not just the error bars, it's a full distribution over the parameters.
Right, at the end we're going to talk about, once you have a chain, what you do with it. Right, which will be basically taking very simple, just take histograms, and then you can say, here's the peak likelihood, and now I know the likelihood as a function of the time.
It also lets you take posterior expectations, because it might be that you don't measure a parameter of your model very well, but you can actually make a very good prediction for some function of your parameters, and you can take that as an example. So you should also discuss that.
Okay, the proposal distribution. And this is the key to everything. So, dumb idea number one. So I start with theta I minus 1, and I will step or choose Gaussian distributed delta thetas. So we start here, and I'm going to...
Can you give us just examples of what thetas might be?
The parameter model. So like last night I was fitting a stellar mass function. So I've got m star phi and alpha, right? Stuff like that. Just anything you want. I apologize for not having those examples like I had last week. Okay, so and I'll choose. I'll have fixed widths of step size. So basically it's just saying that, theta I equals theta I minus 1 plus in the numerical recipes parlance gas dev times width. Right, and I just chose this to be 0.1 beforehand. And this will actually eventually work. It just will take quite a long time to actually converge, and we'll get to the definition of convergence later on, with respect to a little bit more intelligent methods. So, slightly less dumb idea.
Why is it obvious that's dumb? Dumb idea number one.
Let's see.
I don't think it's that
Because you're not gonna be the same amount.
or it's not efficient, maybe.
It is not efficient, which for some people is the definition of dumb. Let's say we're going to look at a two-dimensional likelihood plot, theta, j, and theta k. This could be alpha of the Luminosity function, and this could be m star of the Luminosity function, or something like that, right? And let's say I've got really tight constraints in one axis and really bad constraints in the other axis. And so if I was choosing the same step size in this direction as in this direction, let's say I'm here, and I've got large step sizes in here, and then large step sizes in here, whereas this large step might be in a relatively even part of the likelihood function. Jumping out here, you're going to get to something which has a really bad Kaiser in your model.
The dumb part is not the Gaussian part, it's the same width in all the variables.
Yes,
Okay.
we're going to be using Gaussians throughout.
Okay.
I'm sure there are better ways to, I'm sure there are other ways to do it, but I always just use Gaussians. It's just how you do your step sizes and what direction you're stepping in. not so dumb number 2. Also use Gaussian, but make width equal to the standard deviation of your parameters in the chain. Up to the current step. Right, so this assumes that I already have some number of elements in the chain. Like say I have 50 or 100 elements in my chain. And for each parameter in the chain, I can calculate what the standard deviation is. Right, so that solves this problem in the sense that I now know that the width here of my step size should be much smaller than the width here. Right, so now I'll do something more like this, or like this, or whatever. And I have a much higher likelihood of acceptance for the next step in the chain. Okay, now, what's wrong with this? The thing that's wrong with this idea is that most likely, because you're doing MCMC, you've got correlated parameters. So if I have something which looks like this, where these are the confidence intervals on say x and y, right? I've got large variance in both my dimensions, but they're correlated. So if I use this method, I'll say if I have some parameter here, then the 1 sigma space that I can step in is something like this, and that's also not going to be very efficient for properly sampling the cluster. So what you want to do is so a good idea is use the covariance matrix. Of the chain up to I minus 1. So you're continually updating covariance matrix, at least in the beginning part of the chain. We're going to talk about when you stop doing that sort of thing. So basically the idea here is you get covariance matrix, and then you diagonalize, and then you step Gaussian steps in the directions of the eigenvalues, or excuse me, in the direction of the eigenvectors. Step along the eigenvectors proportional to the eigenvalues. And then you rotate back into the frame of the actual parameters using the inverse of the matrix of eigenvectors, and then you have your new parameter, set of parameters you're going to calculate your likelihood of. So that then solves this problem here, where now I know the covariance matrix tells me that the first eigenvector is this one, the second one is this one, and so now I will be more likely to be sampling properly from the posterior. Questions about how to do this?
Is there some local, covariance matrix? I mean, you could imagine that that's some kind of variable system.
Yeah. So then the next thing up from that is if you have something which looks really crazy, like this, where you've got really strong curvature. So obviously, the covariance matrix here and the covariance matrix here are different, but you can't do something like an adaptive covariance matrix because to be Markovian, Q must be fixed, or else it's not a truly random process.
Sorry, what is Q?
Q is the proposal function. Just think of Q as your method for getting the next step, which means the covariance matrix must be fixed, your eigenvalues and eigenvectors are fixed, your step sizes are fixed, everything's fixed. And only then can you actually...
Your covariance matrix isn't.
Right.
That's, okay, so that then gets me to the next part. Well, any questions on this?
Is that not that expensive to diagonalize a matrix every step?
Well, normally you're not going to be doing 1,000 parameter chains. There are probably even more efficient than MCMC if you've got that. you know, usually I'm doing this for a maximum of 20 or 30 parameter models, and it's not the bottleneck. Okay, when do I fix Q? This is called the burn-in phase of your chain. This is when the chain itself is not, I don't know, relaxed or settled or whatever. You were trying to determine when the chain is now properly sampling from the posterior, and only then can you actually then fix your method of sampling, and then you can actually start using the results from the chain. Some people call this convergence. In the literature, I've seen two definitions of convergence. One is the convergence of when are you properly sampling from the posterior, and the other definition of convergence, which is the one I like, when are you done sampling from the posterior such that you know you have an accurate representation of the posterior, you can stop the chain and actually start using the results. So since burn-in has a name already of burn-in, I'm going to use burn-in, and I'm going to use convergence to know when should we stop the chain. So just if you're going to, if you just look at the chi-square of each one of your models as a function of the step, it'll look something like this. Just you generally do not start at the maximum likelihood place. You start maybe 3 sigma away from that or something, at some random location. And the chain will wiggle its way down to where the maximum, and then it'll sort of even out, and then it'll start doing something like this. So obviously this is bad. This is good. There are a little bit more quantitative ways to do this, but just you should know that just by looking at either the parameter or chi-square of each element of the chain, you can get a pretty reasonable idea of when you are done with your burn-in phase or not. So when you are done, okay, one question that I've always had is, once you're in this part of the chain, should the distributions of chi-square be a chi-square distribution? I also there should be. I've been told that that is not true.
There's got to be some small chance you'll wander into some other valley or something, right? Even in the good phase. I mean, like if you've got 2 minima or something, should you like?
Yeah, that's a complicated issue. If you know there are 2 minima, then you should then be the statistical test I'm going to tell you about are probably not very valid. But then instead of looking at the one-dimensional chi-square, you can now look at chi-squares to make sure that you're actually properly getting the 2 minima. Everything that I'm saying is probably not super applicable if you actually have multiple distinct minima. A lot of the time you'll get minima, but that's just because the chain is not yet converged. And actually there's a bridge here, and you just haven't properly sampled this part of the way. Okay, so before telling you where this division is, I'm going to go to the idea of convergence, which is when you stop using the chain, stop running the chain. Any questions?
We're trying to find the critical point in this chi-squared function, right? So why is it oscillating more rapidly near its?
To be honest, I don't really know. I just find that to be true. When it's in the downward phase, perhaps I exaggerated a little bit here, but like the difference between these steps, since you're going down, you're not really seeing it. Obviously, the probability of going from one chi-square to another is the same everywhere in the chain. So I shouldn't really be drawing that. Basically, I just want to, convey the idea that everything is now pretty flat. You look at the parameters of the chain, they're going to be the same thing. Okay. Convergence. When am I done? When can I stop writing the chain? So, basically the idea of Monte Carlo, Monte Carlo is that the points are independent of each other, which is not exactly true. If you're starting at some position here, you're going to go to some position here, and it'll take some distance. It's almost like a Brownian walk. It'll take some distance away in terms of the number of steps before this point is totally uncorrelated with this point. So there's a correlation length in your chain. But what you want is the correlation length in your chain between the different parameters to be much, much smaller than the actual length of the chain itself. So there are multiple ways to do that. So one way that was in a paper with David that's presenting the affine invariant sampler from the MCMC chain is that you look at the correlation function. Of each parameter. And of course, as we went over correlation functions yesterday, we know what this means. So if I have psi as my correlation function is a function of step, or maybe delta step. L chain is the total number of elements in my chain, or at least in the usable part of the chain. I threw out the burn. Here's 0 and some arbitrary number 1. This delta I is then the separation in terms of placement in the chain, like element 50 and element 52, and if delta I 2, obviously. And nearby points in the chain are obviously highly correlated, and this will decay very fast, and eventually you get to something which is like 0. You want basically the point at which this gets 0 to be, well, we're going to call that a correlation length, even though it's not really a correlation length. R naught over L chain to be much smaller than 0.01. Okay, now you said it was not, it was the area under that integral. There's actually the
technically it's the technically it is the area under, but it doesn't really matter. All these things are heuristics anyway.
Okay. You would then, if as opposed to using the area, if you just use this particular value, you just change whatever your threshold is.
You're also looking for that area has units of number of, because this is delta I, so that area, since it's a wave function, has area. The area is in units of number of steps. So you just want the number of steps to be much larger than that.
Yeah, basically anything where you're calculating what the correlation length is, or the correlation between parameters, just you want that correlation to be 0 on scales which are much, much smaller than the Yes?
So do you calculate this? So I'm just envisioning this big loop, right? And I'm thinking I'm stepping over all these I's. Am I continually calculating this every step in the loop, or do I?
You can do that. It is probably not very difficult to do that. I personally do it as a post-processing thing, where I have a chain that is running.
So you think you're done, and then you go back and prove to yourself that you're done.
Yes. Well, I have a chain which is running, and then I can just take the chain and feed it into any post-processing code that I've written, one of which being the correlation function, and then I can just stop the code when I know it's done. Or you can have this internal.
Okay, so it's writing something out. Okay, so you're not necessarily, okay, I got it.
There's, one of the great things about MCMC chains is it's really easy to do post-processing.
But the answer to my question is yes, like it's you're continually evaluating this function as the chain is running. I mean, not continually, but you could. You could. That's the idea, is that you're building this up as you.
Yeah, it's probably overkill to do it every time.
Okay.
Depending on it's all depends on the number, the length of convergence. All depends on the number of parameters that you got and the complication. If you have really noisy chi-square surface, for example, then things are going to take a lot longer to converge. But thousands to 10,000s is usually a sweet spot. If you've got 20 or 30 parameters, then you're up to 100,000s.
To connect to your last lecture, there's an integral constraint here as well.
Yes,
so the correlation function has to go to 0 inside your chain. So that's why the rule is you want to run much longer than that.
Right. Do not be fooled by possibly going to 0 because your chain is really short.
Similarly, you should study large-scale structure in large volumes of the universe.
Yes, you should.
If we have time, I'll rant about putting estimating luminosity functions in the Hubble alternate field. Okay,
as long as you don't write in the style of Andy Gould, it'll be fine.
I couldn't even if I tried.
And what is this number, 0.01? If you made that 0.001 with your other form?
Yes, even better. Method 2 are multiple. This is what I usually do: is multiple parallel chains.
Wait, so even better? Does even better mean? that you just ran your code longer, or does even better mean like something's better about your process?
It could be one of two. It could be one of two answers. Let's say that you changed the way you did your sampling, and you ran the code the same length, 100,000 points, and the correlation length went down from 0.01 to 0.0.
Same length as you're talking about your binning, your delta, how I calculate my delta i's.
Not how I calculate delta i's. The delta i's here are integers. 1, 2, 3, 4, 5, 6, 7.
Oh, no, I'm talking about the standard deviation, Gaussian distribution, that.
Right.
Okay.
So let's say I went from dumb idea 1 to dumb idea 2, and I have two chains with those two methods. They're both 100,000 elements in the chain. The second one, dumb idea 2, will go to 0 faster than dumb idea 1. Or you could be like, I'm just going to run it longer with the same way of sampling, getting the proposal distribution, and that should go down also.
Okay, but that's still just making your method of getting the answer faster. It's not necessarily changing the answer.
Oh, you should. All of these methods should get once they are converged, hopefully they will have the same answer.
Okay.
If you change your proposal distribution and you get a different answer, then there's something wrong with the chain.
If these provably all give the same answer, if you wait long enough.
Yes.
The problem is there's literally no theorem about what long enough is.
I mean, when you say they all give the same answer, clearly it seems like the step condition, the probability when your likelihood is less. I mean, if you made that the square of the ratios instead of the...
Then it wouldn't be correct. Then the method wouldn't be correct.
So, so when you say all of these things converge to the same answer, modulo what? I mean,
meaning all choices of Q.
Q is the...
Q is the proposal distribution, how you get this delta theta. How you go
Okay,
from one step
so
to the next.
the invariant of that, but
that
No matter
is
what
not,
you put in for Q, you always get.
that is not the same as changing your probability of acceptance, which is what you were talking about.
Yeah.
That's actually screwing away with the whole
So that has to
deal. But if you have dumb idea 1 and not so dumb idea 3, and you ran them both for 100,000, they actually got different answers for your eventual posterior, that just means that probably number 1 you didn't run it. Because you're sampling from the same distribution, supposedly. Okay. Method number 2 for testing convergence. You have multiple parallel chains.
Why do you call these conversions? I mean, I would call this just, what is the correlation length with the chain? And then you take data only separated by the correlation length. And then you check conversions of that sequence. When you calculate something very easily with a conversion done. This is only taking care of that you don't want to take very correlated steps along the chain. Just keep points along the chain. Am I saying this right? Or do you really take all the points in your chain that are next to each other?
Well, you can trim the chain. That is the point of post-processing. And some people do this. Some people do this quite a lot, where they take the chain and actually keep only 1 out of every 10,000 points in the chain. And that will obviously eliminate the point-to-point correlations. You don't need to do that. If you are doing, for people that do that, I do think WMAP does trimming of the chains. But it just seems that if you're relying on that, if that number, that trimming factor is really high, it just means that you have a very poor probability distribution.
You don't need to do that in the sense that all the points are drawn from the distribution.
Yeah, it is okay to have correlated points in the chain. You will still, as long as once again the correlation with the small total size of the
The way
chain.
to check. Okay.
How having correlated steps in the chain you are analyzing for your results is okay, just as long as the correlations are small.
Right, but it could be 1, right? You should take. You're just showing me that the correlation function.
That's arbitrarily normalized. I mean, yeah, if delta I is 1, then yeah, the correlation would be really strong. That's still okay. As long as obviously if nearby steps, if delta I of 1 is more correlated in one method versus another method, then you will have to run the chain. But that also goes, we're going to talk about that in terms of acceptance rate, right? If nearby steps are more correlated, you're more likely to get an acceptance. If neighboring steps are highly uncorrelated, you are less likely to get an acceptance. And then both of these have problems in terms of change variance. There's going to be a sweet spot for them.
But related to Roman's question, the fact that the points are correlated means that at the end of the day, when you have made 100,000 points with MCMC, you don't actually have 100,000 independent points. Right. So there's an effective number of independent points. Right. This helps you calculate that.
Yeah, and I would
but you
imagine
don't have to thin. You don't have to thin down to that number. You can use them all and just remember that your effective number is small.
What's the you gain by keeping these correlated points?
Well, when you then, after your chain is finished, you're going to bin things up in histograms and look at the likelihood functions of your parameters. They're just much smoother. I mean, you know, if you have enough such that you can trim out 5 out of every 6 points and think it's fine, then that's fine. Okay, parallel chains. So, 2 good things about parallel chains. One is that, then you've got effectively a longer chain. You can sum up the results from the different chains. Second is that now you can test these chains using the different chains for convergence. So basically the idea here is that the dispersion of some parameter theta, x or whatever, you're going to do this for all of the parameters in your model, but just for some parameter theta x. Dispersion of parameter between the chains much smaller than dispersion within the chains. This is another way of saying basically that you've run 5 chains, all 5 chains are getting the exact same answer. Right? So if I have 5 chains, here's I, and here's some parameter theta x, and one chain is doing this, and another chain is doing this, even though these are not really moving very much with step I, obviously this is not converged because they're totally different answers, right? What you want is that in some, that's your first chain, and your second chain is doing pretty much the exact same thing. So the mean of the first chain is this, the mean of the second chain is this. So you're actually, what you were doing here is the dispersion of the means. So if I've got 5 chains, there's the means of all 5 chains. You do the dispersion amongst the 5 means. Versus the mean dispersion of each of the n chains. So once again, so this would be external dispersion, external, and this is going to put the internal dispersion.